Jay, did you guys figure out are you going to use multibody or not use multibody? Depends how many degrees of freedom in your vehicle.
I don't feel like I can't be sure about either method.
How many degrees of freedom in your vehicle?
Six.
It's just a lump mass with interesting thrusters. It's just a single brick flying around with interesting lift and drag. Then I think you probably won't get that much out of multibody. All the interesting stuff is the actuator model, or the force models.
Yeah. Is it possible to input a model for visualization only and then?
Yes, definitely that. Yeah, definitely that. It's a little harder. Like rigid body tree, it was really easy for that. The multibody's a little bit harder, but it definitely works. Yeah.
Oh, yeah. Just by the standard.
Okay, welcome back. So last time we introduced sort of a new set of tools for motion planning that had the property of somehow at least probabilistic completeness, that if you have a start and a goal, right, you have a start state and a goal state, then the complete planners would be guaranteed, at least with probability 1 as time goes to infinity, we'll find a path if it exists. So that's great for if you are really solving a motion planning problem where you are starting at exactly one state and need to get exactly to some goal state, then that's a super powerful set of tools that we can use. I agree. I tried to say that there are some limitations in applying it for systems with interesting dynamics. Certainly in the kinematic space, they are very successful and widely used. The problem is, for real robots, you're never just in one preordained state and then wanting to find a goal. Probably we need something like feedback to make things go well. So what I want to talk about today is how do you take the ideas that we started with last time and try to grow them into something that we could really run on a real robot. Now, the natural idea you could, if your planner, your randomized planner, which is finding paths, by even sample-based methods or by the mixed integer methods, if your global planner is fast enough, then you can use it in a model predictive control approach, right? So plan every time step which we'd call a model predictive control. You can certainly do that. Now, if you're doing that with a completely random method, you'd probably like to do something to ensure that you're not doing completely different things on every time step to sort of regularize that out, and that's always true. We affectionately talk about the RRT Dance, right? So it was visible in great form at the DARPA Robotics Challenge, for instance, when one of the robots, which was had a great range of motion, it was like a marvel of engineering. By watching the chimp robot get out of the vehicle, someone told me it wasn't even an RRT doing the work, but it was classic RRT Dance, where the robot kind of went, like did sort of everything it needed to do, but, and twisted itself in all kinds of contortions and eventually got out of the vehicle. And you can't, it was just shockingly impressive and good, but it looked a little crazy too. So, and there are papers that are written that talk about, I have my simple robot, I'm going to reach to a target, and the robot goes like this and reaches to the target, and how do I not do that? So there is this thing called the RRT Dance, and maybe if you're going to try to use it in a control loop, getting rid of that dance and smoothing out the trajectories is important. So this is one idea, and there are a bunch of ideas sort of in this space. So more generally, if you've done a lot of work to grow out a tree of possible paths through the space, there's also the idea of growing out a roadmap. In fact, that actually came first, where maybe you don't just grow a tree, but you grow a graph across your state space. So if I have a start and a goal here, that's the one way to think about it. Or I can just think about lots and lots of paths that take me from lots and lots of places to lots of other places. And if I can search through at runtime and try to find myself in a new configuration, maybe there's lots of different sort of, I can reduce the continuous dynamic domain search problem into a graph search problem if I've just sampled lots of nodes and tried to connect them as much as possible to everything else. Then, there's notions of slightly different data structures instead of the tree that you could store that are amenable to online computation. There's also, I think, these are my straw men, I'm sorry to say. These are, I want to, there are some natural things that fall directly from what we did last time, and I want to mention them quickly, but that's not what we're going to spend most of the time on today. There's an idea of RRT Star, which I think is particularly valuable for this. So, and in general, backwards or bidirectional trees which I think is a particularly good goal. So in the example I showed last time of the bug trap, we had a start inside, one of these points inside here was our start, and it eventually grows out these very complicated trees that will eventually find their way to the goal. But imagine if you flip this problem around and said that actually this is my goal and this is my start. I could have done that just as well, right? I could have tried to grow the tree backwards, especially if it's a kinematic planning problem and there's no sense of having to go in one direction because of dynamics. Imagine that was my goal, and I just said, try to find all the initial conditions that could possibly ever reach the goal. So I'm going to grow the tree backwards. Then to some extent, this tree represents a feedback policy, if you will, from lots of different initial conditions. It tells me a feasible path that will take me back to the goal. So if you turn the problem around and think about it backwards, then maybe you can think about these RRTs as an approach to doing feedback design. Okay. RRT Star is a variant that I didn't discuss and won't discuss in detail here, but it's a nice variant where it tries to constantly rewire the tree so that it's optimizing some objective and tries to get rid of these crazy kinks in the RRT dance. And the standard picture for that is this. It does an RRT to begin with and finds a path to the goal, but it continues to add more and more nodes and deletes edges as better candidates are found so that it slowly converges to something that really does feel more like a sample-based optimal policy. Again, this picture is from the start to the goal, but if you just flip it backwards and think that this was my goal and any of these other potential leaf nodes, I guess, are my start, then really that gets you thinking towards maybe I've got this sample-based view of the world that could bring me towards building a feedback controller. Okay? But there's something the reason that these are my straw men, I actually think that's a good idea, and you could try that. But there's something that's not quite right about this, or there's something that doesn't, I think, solve the fundamental problem. And it's rooted in the fact that the vocabulary here is trajectories in state space. okay? It's the fact that we're thinking about lots and lots and lots of single solutions. And there's really no good vocabulary. In this vocabulary, there's no really way to talk about uncertainty, disturbances, robustness along single paths. These are single solutions of the nominal system, right? Control, the other things we talked about with control, we had a natural way to think about, commonly Lyapunov functions, or we will do more and more robust feedback, starting actually on Thursday. We'll talk about robust feedback synthesis. Those notions fit naturally, and you can do planning under uncertainty if you go into a different space, and there's ways to make this work, but this picture of just having trajectories everywhere somehow isn't quite what I want to talk about today. And let me say it maybe this way. So imagine you went up to Mark Rabert, who runs Boston Dynamics, and you said, I know you guys have been working really, really hard. You've got a beautiful trot gate, you've got a beautiful bounding gate, you've got a beautiful, you've got all these controllers that work really well. They're super tuned up, they're robust to noise, they've got your sensor errors or whatever. We're going to throw those away and do, this kind of planning and execute those kind of plans, right? I can picture the look on Mark's face if you were to say that. He's not about to do that on his robots, right? So why would, Boston Dynamics not execute quickly planned trajectories at their lowest level of control? There's something different about designing feedback controls at the low level that sort of isn't quite captured here. Okay, so that doesn't mean that we're dead in the water. I actually think there's a beautiful relationship between these ideas where we want to do, I think this randomized planning is a really nice way to sort of grow out and cover the whole space, okay? But there's also something good and natural and good about having the primitives not be little edges and trajectories, but being feedback controllers. So what we want to do today, feedback motion planning, is this idea of can we compose lots of different feedback controllers together, potentially in a random way, okay, in order to somehow get the best of both worlds, right? So we'd say, I'm just kidding, Mark. We're going to use your trot controller. We're going to use your bounding controller. We're just going to find out where it works and turn it on and off, in really clever ways in order to make it work in domains you didn't test in the lab, right? He'd still probably tell me to go hit the road, but I'd at least have a longer conversation with him. Okay, so instead of talking about this in the abstract, I like to think about this. I like to make it concrete with another sort of toy problem, another simple system that I think is it's actually the one that was used in the first paper that got me thinking about this, and it's just simple and good. And it's actually about juggling, right? So I'm a horrible juggler. I was debating whether I should even bring this. I'm sure there's probably someone in the front row that could do this much better than me. But think about the complexity of juggling, right? These are all very different weight. This is, the dynamics of my hand are pretty complicated, right? I've got timing things I'm worried about. I've got dynamics things I'm worried about. How am I going to write a feedback controller for something as complex as this? There's contact mechanics, right? There's probably not aerodynamics, but a little bit of aerodynamics. So if you take one thing away from this class, one of the things I've been implicitly preaching throughout the semester is the value of simple models. So the answer is, if you really want to think critically about juggling, find the simplest example that you can write it down and start thinking about. And the simplest version of juggling is actually a one-dimensional ball. It's constrained to bounce on the straight up and down, and it's a one-dimensional paddle that's going like this. Let's start there. Okay, we actually get pretty quick to the more complicated version, but this is the way to start. This one was by Martin Buehler and Dan Kodacek. Martin was he went on to build Rex, and he was the lead engineer on Big Dog at Boston Dynamics. And he was at Disney after that. He's done lots at iRobot. He's done lots of cool things. But when he was a grad student, he did line juggling. Okay, so you've got a paddle that moves up and down, and we're going to find some coordinate like in the middle here. We'll call the zero plane, and we'll here, and the height of the ball we'll call B, and the location of the paddle we'll call R. So my state space I'll say is B, R, and then B dot, and I'll pretend I have direct control of the velocity of the paddle. Okay? We're going to assume collisions are instantaneous. And elastic collisions. Not so fun if it's inelastic collisions. Be a one bounce act. And so there's some coefficient of restitution. Okay, so, yeah.
Wouldn't it be more realistic to have no elastic collision, since that's what you're doing when you're juggling? Right? Like you kind of are catching the ball and throwing it back up.
It's true. So this is the paddling more than juggling. You could catch it on the way down and then bring it back up. You're right. I discarded that too quickly, but it's not quite as simple. But I bet there's a similarly elegant solution. Yeah, that's totally fair. In fact, it would be just as interesting of a problem. More interesting of a problem, maybe. Okay, but let's paddle first. Okay. So this is a relatively high-dimensional thing if we're going to try to use our graphical analysis. One of the observations that started this line of work, and ironically, this line of work, the juggling work, Dan Kodacek, I think I've got the order of this right, but Dan Kodacek is more on the theoretical side than, let's say, Mark Rabert, but he was fascinated by the hopping robots that Mark 80s. And he was trying to understand why, Mark would talk about these intuitive controllers. I'm just going to push energy in at a certain, on a certain schedule. Of course, it'll hop higher. He had a very intuitive way to think about that. And Dan wanted to understand more rigorously why those controllers were stable. And to him, actually, this was the way he started thinking about the hopping robots, okay? Which is maybe why he did the elastic version. But, so this is almost a hopping robot, okay? But he went on to focus on juggling for a little while. And there was a really nice observation that simplified a lot of this. So you could, of course, it's not hard to integrate forward the equations of motion of the ball. But if you can sort of, the impact conditions could be arbitrarily complex. And they wrote down this idea called the mirror law. Which is that you could impose in your controller the R of t, basically my trajectory was the mirror image of the ball trajectory multiplied by some gain k. So what does that do for you? Well, if you calibrate it the right way, if I've written my coordinate system like this, first of all of the impacts will always land when the ball is at the line, right? And then it just goes away, right? And not surprisingly, the closed loop system now has a very simple return map, and we're going to be able to plot the Poincare map of the cycles of this thing very nicely. Okay. So if you were to plot this collision to collision return map, then you get something that looks, the way I've parameterized it, this is in sort of the negative. If I write B dot at the nth collision versus B dot at the n plus 1th collision, then there is a fixed point at 0. There's a line of slope 1, okay? And so this is the unstable fixed point in this. But the return map has some characteristic shape like this, okay? And there's a stable fixed point here. And Martin and Dan went through and showed that if you choose K properly, you get this nice Poincare map that you can understand graphically. And because it's a one-dimensional unimodal map, they were able to show that this is essentially globally stable. Essentially because there is a point of measure 0, which is when they're actually stopped, which is also a fixed point. But every other initial condition will eventually go to a stable hopping height, just by choosing K and going like this. It is really the precursor to the analysis of why the hopper bounces at if I put a fixed amount of energy in, for instance, it'll go to a stable hopping height. At some point, the losses from the coefficient of restitution, cancel out, and I've got a stable fixed point. Okay, so that's sort of, the fun analysis. And of course, they started to build something like this. They did build a line juggler version, but I think the first video I was able to find was actually one version harder than this. So now we do 2D juggling. So you want to allow the ball to move both in X and Y, X and Z, I guess. It's going to go up and down, but also side to side. And it turns out you can do that pretty nicely in practice, even if you just have a paddle, still with a 1 degree of freedom paddle. I still have my place where I'd like all my collisions to occur, but now the ball is parameterized by the X position of the ball and the Z position of the ball, let's say, and the paddle is parameterized by theta. You can still do a mirror law type argument, okay, and that will stabilize BZ, but it doesn't stabilize BX. The way that you stabilize BX is fairly simple, and again, analogous to what we were talking about in the hopping case. But the rule, which you can bear out with analysis in this simple enough system, is that, what is it? If BX is too far this way, then you'd like to hit a little bit lower below the line, and it'll add a little bit of velocity in that direction, right? And if the ball is a little bit farther on this side than you'd like to hit it a little early, and that'll send it back this way. And a very simple modification of the mirror law, which adjusts the time of the collision in order to stabilize, can also simultaneously stabilize both BX and BZ in its hopping height. Okay, and that was the first robot video that I found from their work here. This is the two-degree of freedom juggler. So the way you do 2-degree of freedom juggling is you get an air hockey table, you put it on a slant, okay, and you pretend it's a ball that's constrained to be in the vertical plane. Okay, so it's not quite, gravity is not quite 9.81, but that's okay. And what you'll see is that they stabilize not only the hopping height, by the way, it's trivial to just do it twice every cycle, right, if you have two balls, but it stabilizes the X location as well as the hopping height. Are you convinced? It's still an experiment. It's not a perfect, like, I think they have I think that's probably the red line that they're trying to stabilize too. It's pretty good. Right? Pretty good. And that's also, that's a bright yellow ball on a non-yellow table, which made computer vision tracking easy, Okay. You can take that same idea, and really doing it in 3D is not much harder. Now I suddenly have to, if I want to regulate the position, so this way out is what we've already done. Now I also want to regulate it in this direction. I can just twist the paddle like this and stabilize with the same technique in 3D. That's when Al Rizzi joined the team. This was in the basement of the AI lab at University of Michigan. There was a time when I was doing a year up on the other side of that curtain for a little while.
Was that really annoying?
It was actually off by the time I got there. This was the real experiments predated me. But I always wondered what was behind the curtain. Okay, so that's pretty good. And then they started getting fancy, and they wanted to take these low-level feedback controllers and start doing, juggling skills, right? So I won't demonstrate that, but actually Noah Cowan was like a really good juggler who was one of the follow-on grad students with Dan Kodacek. I mean, he could juggle 7 clubs or something like this, and do all kinds of tricks. And so they wanted to take these ideas and push them more and more towards more dexterous, more advanced juggling. And if you look at the paper, they talk about writing similar simple feedback controllers for instance, palming. If you could sort of match velocity and then slow down in order to palm. You could do a pass from side to side. You could. They have a whole list of different. I didn't write down the list here. But then it was not too bad to sort of write down feedback controllers for the individual pieces. And this is when they got to the point with a very simple system, easy to think about, clear-headed, right? How do I take all these simple feedback controllers that I've already got? They're parameterized fairly simply. Like I can run my palming feedback controller over here, or I could run it over here. It doesn't really matter where I run it, right? I can fairly simply parameterize and change the hopping height for a couple steps if I want. There's a whole family of controllers that come out of this recipe. How do I take those and compose them together in order to do more complicated skills? Okay. And the picture they drew was really important. So this is the one where they started doing more tricks. So there's the palm. And they had a launch also. And then do I have the rest of them? Yeah, I guess I don't have the rest of them. But the picture that they drew and the paper that they wrote was titled Sequential Composition of Dynamically Dexterous Robot Behaviors. And, not a new picture for this class, but this is sort of where I saw it first, where I liked it first, was the idea that for every one of those, not only did they have a simple controller, but they had a simple Lyapunov function, right? And that Lyapunov function, some positive definite function, which goes down over time, has an interpretation in state space as a funnel, right? So if the x, y coordinates here are my state space, and the z coordinate in this picture is the value of my Lyapunov function, then the thing that my feedback controller does is it takes a relatively large range of initial conditions and it shrinks it down into a smaller range of a stabilizing controller has this effect of taking a large range of initial conditions and bringing it down to closer to the fixed point, let's say smaller initial conditions, okay? And Lyapunov functions give you a mechanism for actually talking about that. And then they said, okay, well, we know how to make simple Lyapunov functions like this that have simple regions of attraction like that on the ground, right? But what we really want is like some uber Lyapunov function, which is good, good for the entire state space, everywhere that the robot could possibly operate, and maybe it's really complicated, and we don't know how to write that controller. It's just too complex, right? But we'd love to have this thing that's sort of, capturing the entire obstacle-free state space of the system. So the picture that they drew was, well, what if we took all of our simple controllers and fed one into the other, and slowly composed those controllers, into a larger region of attraction in the state space? And this was this really defining picture, I think, of trying to fill up the state space with lots of simple controllers. So they were missing some of the tools that we've been talking about in the course here. So once it went to the real experiment, the more realistic parameters of the robot and the like, they didn't know about sums of squares back then, but they were able to do a lot of. It was a simple enough experiment. They could do a lot of sort of repeated testing and get experimental, empirical regions of attraction for their system. So this was a scatter plot of different collisions, of points for estimating the domain, the region of attraction of one of the particular skill parameterizations of the skills. And they basically did this enough times and said, yeah, right around there is the region of attraction, right? Which is good. I mean, that's awesome, right? Maybe it's hard to do that for a bigger, complicated system, but that's the beginning, right? So empirically estimating regions of attraction, and then they really showed this picture of saying, okay, I'm going to do tricks where, for instance, I want to pass under a beam, right? So there was a beam in the lab, and they would go and they'd go either under it or they'd go over it and catch it on the other side, and it was just an obstacle in the middle of their juggling workspace. And they would compose all of those skills with a bunch of known stable ROAs. They would turn on another one where the outlet of this funnel would land inside the inlet of this funnel, and shift until they did some different skill to get over the beam, and then come back down, off they went, right? It's a really, really beautiful idea, I think. When you ask Al Rizzi and Dan Kodacek about how did you come up with this idea? They say, oh, we didn't come up with the idea. They talk about Lozano Perez and Matt Mason. This is the 1983. Some people just call it the LMT paper, which is pretty good. If people just can use 3 letters to describe your paper, and then you didn't use those 3 letters, that's pretty good. And they talked about, in the kinematics place of trying to do peg and hole problems, talking about pre-images of these different tasks. If you took a certain approach with your peg to the hole, then the straight up approach has a pre-image, the initial configurations that will successfully land with the peg inside the hole. It looks like this. If you come in with a different velocity, it comes like this. And they were already computing these sort of pre-images, these funnels, for the very kinematic thinking of the task. And they were already trying to chain them back. They did this pre-image back chaining, which was to try to fill out the space with with plans that would come up and take the output of the post image of one skill and put it into the pre-image of another skill. And they've been talking about that for a long time. They even talked about uncertainty in this, because the peg and hole problem is rich in uncertainty. Small amount of uncertainty can cause big problems if you're not careful. And the best strategies for peg and hole embrace that uncertainty and come down and have mitigation for that uncertainty. So this is their idea of how a pre-image changes if there's uncertainty in your motion. That if you have to make sure that you land at the bottom despite uncertainty, then it shrinks your funnel going backwards. Or if you take the opposite, sort of the weak pre-image, that you might get lucky from any one of these states and find yourself into the goal. But if you absolutely have to get into the goal, then you better be inside this state. So they already baked in this notion of sort of robust funnels, robust things way back in the day. Okay, So we've already been talking about this a little bit, with all the tools, but now that we've seen RRT and everything, and this notion of how would you take a trotting gate or some other controllers, then you can see maybe how we put it all together. And let me remind you about that LQR trees, the picture I showed you before. So if your recipe for creating the individual controllers was just LQR, and your recipe for creating the regions of attraction instead of sample-based stuff was now sums of squares, then we already have a pretty good sense of it, right? So we take our initial condition at the upright, we compute the LQR controller, we compute the region of attraction. Now the randomized motion planning comes in, okay? So like in RRT, we'll pick a random point in the state space. This time, if it's already inside a region of attraction, if it's already inside the gray region, we can just reject it. So like the RRT, we can think of, by rejection sampling, choosing, having our sampling distribution now be changing over time, but it is uniform in the currently not stabilized regions. Right? So I will have sort of, by rejection sampling, I'll have an equal probability of picking anything in the white region and 0 probability of picking something in the green, or in the gray region. Okay, so I pick a random sample. I picked one here. I'll do trajectory optimization to try to get this back to one of the other parts of my tree. That's exactly like the RRT, but because, like we said, the extend operation for dynamic systems is hard, we're going to use full-on trajectory optimization to do it, in this case. Full-on trajectory optimization with SNOPT for a nonlinear system, let's say, is not guaranteed to succeed. So what we have to say is that if SNOPT says infeasible, then we'll also reject that sample. Okay? So wait until SNOPT gets lucky and finds a solution, okay? And then now we've got a blue trajectory that will eventually find its way back to the original tree. And we can compute the funnel for that trajectory too. Remember my fun little video I worked really hard on, so I'll show it again. Okay, but the cool thing is now it has this notion of, like the sample-based planning, this notion of probabilistically filling up and trying to cover the entire state space. And I think it sort of realizes the picture that Burridge was trying to show in his paper, where now I pick another sample at random and add it, if it's in the gray region, I discard. I do that a bunch of times. Every time I add an edge to the tree, you have to do some work to show that for any point in the white space, because even though trajectory optimization is not complete, you want to have some probability of it succeeding in adding an edge. There's some work to be done there, but you can make that happen. Okay, and then the statement is that as the tree grows, now my sampling distribution becomes the white regions. I will eventually pick some sample inside the white region. It will eventually find a connection to the tree via trajectory optimization. And if that was a stable, if it's possible to get from the white region to the tree, then it'll eventually find it. And if it was stable, if it was possible to get there, there's an arbitrarily small stabilization that will work for this, and we'll eventually add a new gray region into this. So as time goes to infinity, you'll eventually fill the state space. Okay? So the notion we had before was probabilistic completeness of the planner. If a trajectory exists that gets me from point A to point B, then I will eventually find it with probability 1. The property that we can say about this algorithm is something that we called probabilistic feedback coverage. Okay? Which says for any x that is inside, that for which a path exists to get me from that x to the goal, it will eventually be inside the region of attraction of my controller. And the way to think about this, I mean, we're approximating the reachable region, the initial conditions that can possibly eventually get to the goal, with ellipses, which may or may not be very efficient representation for the true reachable set. But we can always eventually make enough ellipses that will, they might have to be arbitrarily small to get the last little nooks and crannies out, but we can always eventually fill the space. So this is a Cookbook example that we made to try to show that picture, which is where we know the sampling distribution here is this cyan region, and we've constructed a system to have a known region of attraction that was on the bottom half of that red line. So there is no way for the system to get from here to the goal, but we'd expect everything below the red line to be able to get to the goal. And as the algorithm proceeds, it gets more and more dense samples of these little funnels that will eventually approximate that straight line and that reachable set with ellipses that will eventually get you to the goal. Okay? So again, you don't have to use LQR, but LQR has the property, right? Think about what was missing from the Burridge part. If you need not only to compute the region of attraction for a given skill, but we need somehow a recipe to, if there's a place I want to get to over here and a set of controllers that I can pick from with some parameters, how do I generate a new controller that's going to land me inside my existing region of attraction? That's a hard thing in general, to just magically find a controller that's going to accomplish that task, especially if they're arbitrarily parameterized. So this recipe of trajectory optimization plus LQR stabilization somehow filled that gap. It's one way to fill that gap. There are other ways. Okay, so that's an idea, and this is when I showed early on, and I said, "Don't worry about LQR trees yet." Right? This is showing it playing out on the cart pole. And even though, I actually don't know a better way to write a sort of global stabilization for this cart pole, given that it has, these hard limits on the x-axis, in order to get what we think is pretty much every initial condition possible for the cart pole to eventually get back up to the upright. I guess there are more conservative ones. You could, if you're close to the rail, you could always just let it fall, wait till the system comes to rest, and then slowly go to the middle, and then do your thing from the middle, and as long as you don't hit the rails. But I guess maybe that's less satisfying. Okay, so I showed this one before, but when I was looking for my slides through this, and I found this video that I hadn't seen in ages, and Joe did such a good job of it. So, and it told the story way better. So let me just show it, a part of this again. You remember the perching story there?
Acting on the vehicle. Flow visualization reveals complex fluid flow behind the aircraft, which we model using time average static lift, drag, and moment coefficients. To design our controller, we first generate a nominal flight trajectory using nonlinear optimal control methods. We then stabilize this trajectory using time-varying linear feedback. Using recent results in semi-definite programming, we compute the region in state space for which this local controller is valid. To overcome the local nature of our feedback law, we increase the size of the initial condition set by combining multiple stabilized trajectories together and creating an LQR tree. To test our approach, we first launch the glider from a wide range of initial speeds and demonstrate that the controller is able to stabilize this large set of initial conditions. Finally, we demonstrate the robustness of our system by throwing the glider by hand. Our results demonstrate that the LQR tree approach can achieve incredible robustness to initial condition variations.
So maybe your eyes are trained enough now to see the pretty significant deviations in the flight trajectories of those different, right? Sometimes it has way too much energy, it has to bleed energy and come out. You see there's a little hook that has to catch the wire. That one's coming in way high. Right? All right. So I was happy to find that again. Okay, there's some details though that make this stuff work, and I didn't cover them before, and I want to fill in some of the details. Okay, so. Because we're going to try to push this, farther yet, and the devil's in the details. So, imagine I have my system, which I've now made in my error coordinates, my time varying linearization approximation of it. And I've got my time-varying LQR controller. And my time-varying Lyapunov function. Even this is time-varying. Okay, so for the linear system, we know that this is going to go downhill. This is going to be strictly less than or equal to 0. And the original question that we wanted to ask was, does this always also go downhill and prove stability of the nonlinear system? But the operation I need for this feedback motion planning to work is a little different than absolute stability, right? Now, the details are, I have a trajectory, call it x0 of t, defined over some finite time domain, right? T's in 0 to t final, let's say, for each particular trajectory. What I care about is that the final condition, there's some sub-level set of j at time capital, at time tf, has to be inside my final condition, right? I want to find, let's say, a row of t such that I want j of x dot to be less than or equal to rho dot. I'll make that explicit in a second. I'd like j of x t final less than or equal to rho t final to be inside my next controller. Okay, so I do care very much that the outlet of this funnel, when it's done, is some sub-level set of j, which defines some ellipse if my j is quadratic in this case. It needs to be inside another ellipse, right? That turns out to be a simple constraint to write. Ellipsoidal containment is something we can write with convex optimization. That works out okay. And then the conditions that I want here is I want to find a sub-level set that could stretch or shrink over time, but what I ultimately care about is that everything inside this sub-level set ultimately lands inside that final condition. That is different than saying that all trajectories inside here will converge to the if I have the nominal trajectory here, that's great. Asking for absolute stability or convergence to this single trajectory is a stronger condition than I actually need to build a funnel to grow my feedback controllers back. Okay? All I care about is finding the biggest volume here so that every trajectory lands of the outlet in the inlet of the next funnel. okay? And there's a reason why that's super important, okay? One of the problems is that I'm getting these trajectories out from a motion planning system. So this is my x0 of t. It's a numerical approximation, sometimes a pretty coarse approximation. It's probably, once scrutinized by algebraic techniques, not actually a perfectly feasible solution for the real dynamical system. It's some cubic spline, sparse cubic spline approximation of what the real solution trajectory looks like. If I actually ask V to converge to this everywhere, it's going to say no, okay? And that actually that'll break the sums of squares tools. Okay, so the condition here of saying, what I want to say is, on the boundary of this funnel here, I don't actually care what happens on the inside for now, but there's I want to be able to find some funnel, which maybe we can agree, if rho is a scalar, that the funnel jx of t less than or equal to rho of t, this defines a time-varying funnel, where this is a positive scalar. That'll define some shape that's level sets of an ellipse over here. And I'd like to find the biggest rho so that all these trajectories land inside here. My claim is, and with a little bit of thinking about it yourself, I think you'll be able to see, this is the condition that I want, is that when j of xt equals rho of t, I need this to be going, I need j dot to be going less than rho dot, okay? Normally we say for all x less than or equal to rho, that would be saying I'd like my stability constraint, I'd like to be a valid Lyapunov function everywhere inside the funnel. Now I'm saying only at the boundary where j of xt equals rho, I must have that the Lyapunov equations are telling me that I will go inside or stay along the boundary of the funnel. Okay? All right, so that's an important difference, and it talks about, this funnel now is a finite time invariant set. And that is the minimal requirement for composability of these funnels in the feedback motion planning case. Is that clear?
Is rho a polynomial?
Rho is typically a polynomial in time. Yeah. So I will typically parameterize that again as actually a piecewise polynomial. This can be another cubic spline, for instance. And for each segment of the trajectory, both in terms of x and rho, we line those up to have pieces at the same time. We can say something specific, and then we verify each chunk separately. Good. Okay, so that's sort of the best recipe I can give now for things like acrobats and cart bowls. It sort of pulls together all the pieces that we've talked about from trajectory optimization and sums of squares and randomized motion planning. And it does, I think, gives relatively strong tools for probabilistic feedback coverage, okay? There's a few more details that maybe are worth mentioning. So like I said, the extend operation in the RRT, if I pick a random sample here, I want to now set up a trajectory optimization that's going to try to find a path back to the goal. Okay? I said in the RRT, it feels too expensive to do a trajectory optimization every time you want to add a little edge. So some people have talked about that, but people typically don't do that in practice. The nice thing is that the LQR tree solutions, because they're picking up big volumes of space and you're only adding trajectories outside of those volumes, you end up with a relatively sparse tree. So you only have to do a handful of trajectory optimization problems, and it's therefore somehow it switches the cost, or maybe it's just because the sums of squares cost so much more. I don't know, but somehow the cost is relatively okay to do trajectory optimization instead of some naive forward projection in order to make these edges. Yeah.
Why do you optimize to the goal instead of to the nearest funnel?
Awesome. So that's actually a super important point. So the distance metric, remember, is bad. So what you would often try to do is say, like, here's the closest point in state space, try to draw a straight line here, and the system will say, I can't do that. Having formed the trajectory having decided that we're going to use trajectory optimization, there was a really important twist on this, which we formulated a trajectory optimization which says the initial condition is my sample point. The final value constraint is you're somewhere on the tree. My initial guess is a straight line to the closest sample, but as the optimization progresses, it's allowed to walk up and down the tree in order to connect. And the objective function there, or the constraint that we add, is 0 everywhere along the tree and goes up away from the tree. To the point where it can even, if there's another branch of the tree over here, it could even hop over and connect up here if it needed to. That made a huge difference in actually being able to succeed in making attachments to the tree. Yeah?
I feel like this is a stupid question, but why, I don't understand why you need the funnels. Like, why can't you just use the trajectory optimization to get from points that are a little off your goal, and then get that point, and then use the trajectory optimization to get somewhere on that curve?
You could do the same thing without funnels, but how do you know when you're done, right? So you're going to have lots of, my claim is that you're going to have many, many more trajectories, first of all, to fill in. You're going to start feeling the cost of the trajectory optimization more. And the real thing is, how do you know when you're done? That's one question. And the one that I'm about to talk about is what happens if there's uncertainty in the system or robustness. There's no notion of, along a trajectory, talking about uncertainty. There is a notion, though, so basically a trajectory cannot be an invariant set to an uncertain system. But a funnel can still be an invariant set. I can still give a guarantee that even if the wind is blowing, if I start it in here, I'll stay in here. It'll change the size of my funnel, but this is somehow a more fundamental object for reasoning about uncertain systems. That's a great question. Okay, but I agree that this recipe of just connecting with trajectory optimization up and down the tree, that works for, even if you don't have funnels, and it actually works fairly well. It's just you pay a large price for calling SNOPed every time you add an edge. So it works best, in my opinion, when you have only a sparse tree because of the funnels.
Why we don't, so I think so that's why we don't stop when we move into a funnel, because so you mentioned how we find the closest point to our random example, but and so we don't know to stop as it is.
Nice, okay, good. So there's, I didn't interpret the original question as that, but it might have been that, and I answered badly. Why not just go into the funnel and then full on stop?
Yeah, and then
So I actually have, at the goal I have the LQR solution, which is the Riccati equation. I work back here, I have a Riccati equation that's defined for the time-varying linearization along here. I have it defined everywhere here, and when I add a node to the tree, I pick up that time-varying Riccati equation and continue to integrate it backwards along the time, okay? So if I were to stop here, I don't actually know how to start my TVLQR. Like I don't have the Riccati equation continued. That's maybe a technical thing. You could probably get around that. But more fundamentally, I think that you don't want to be just at the edge of the trajectory. You want to somehow land in the middle of the funnel so that your controller has some margin in order to sort of land. So landing in the middle of the optimized funnel seems more natural. The burden, though, is it means the RRT's completeness comes from the fact that you're eventually adding arbitrarily short trajectories. That is not true anymore here. I have to be able to add trajectories that are at least as wide as my funnel. So the proving that that's complete is more So I think it's harder to, so it's not hard to say something, and the thing we said is fairly weak, but it's a larger burden on whether it actually works. And the stupid thing, so you can chuckle at me here in a second, but so here it happens that SNOPT actually is a complete planner. You just have to start it with random guesses enough times. And with probability 1, as time goes to infinity, if you start with random values, because it's got some probability of converging, if you've guessed the solution close enough to the real solution, it will converge. So you actually can talk about a probabilistically complete version of SNOPT. It might be horribly inefficient, but it does have that property. So eventually we will add a trajectory that will go across that margin if it exists. In practice, it's not that stupid. SNOPT is actually quite good at finding these solutions. And so it fills it up pretty quickly. There's a few things, yeah, go ahead.
I was just going to say, in practice, you don't have infinite time. Just some kind of metric for each enough.
If you, oh, sorry, okay, you meant a different thing. Let me answer what I thought you were going with, because I like it. So if you land at a fixed point, then you can think of every one of those trajectories as being defined ultimately at infinite time and actually stabilizing to the goal. Right? So each one of these is finite time trajectories, but the last one ends at a fixed point. So everything becomes good, and we could talk about stability again. I realize now that's not what you were asking, but you said infinite time, and I went there. Sorry. Okay. So now I have a finite amount of computation time, right? And I want to fill. So it's the same as a RRT. Basically, you up to your patience. You try to fill the space. You go and execute. We have versions of this. In fact, the cartpole one was a simulation-based one, where basically, once you put it on the experiment, if you ever found yourself outside the funnel, you could still, these funnels also produce a distance metric over the state space. They have a natural covering where you can ask everybody, all the neighboring trajectories, what do you think the cost to the goal is, right? I only have a guarantee inside the funnel, but even outside the funnel, I can still say, if I were to execute you, what would you think the cost would be? I'd say X transpose SX for this solution of S. What do you think the cost would be? S transpose SX, okay? So I'll pick the one that is most optimistic about my cost, and I'll start executing. I'll do trajectory optimization to try to connect back to that and the like. And in practice, you can add new funnels to your tree while you're executing on the robot if you ever found yourself out of that, and trajectory optimization will often still work on the fly. And we have some ways where you can argue that that's actually a robust thing to do. We took in the extreme, you could never call sums of squares to begin with. You can only do this sort of on-the-fly approach, and that's what the simulation-based LQR trees were. Was that I add a trajectory. I assume its funnel is infinite. Every time I go to start a new execution, I pick the funnel that I'm inside. I start executing it. If it lied to me and I failed, then I crop the funnel. Right, and then I add a new trajectory to do it, and I can sort of iteratively on the fly build these things with a simulation-based version, and that has appeal for being out in the wild. And every time I've experienced a new trajectory which falsified my previous controller, I make it better, and it just keeps improving. Okay, so there's a few things that I really don't like about this. I think in the case of sort of designing full state feedbacks for acrobats and cartpoles, and there's one more picture here. Even for walking robots, I think there's something sort of good about this. Right, so there's the compass gate. We can compute the regions of attraction to the stabilizing, the periodic solution of the compass gate. It looks like this gray region here, okay? That's the projection from a higher dimensional space. That's the funnel of the compass gate, the nominal compass gate, with a torque controller at the hip, okay? Now Now we want to make the compass gate more stable. Our simple LQR stabilization was only so good, but I can, if I find myself in a new configuration, then I can do trajectory optimization. I can connect back to the periodic solution at whatever point, and then grow back a funnel, and eventually sort of go up and fill the space. And to me, even for the pendulum, but especially for the compass gate, there's something sort of inherently good about that. So I think maybe we do have lots of controllers. I've probably got a reasonable controller for periodic walking, and for small perturbations, I'm probably just executing that controller. And if something comes around and knocks me off, I'm probably going to turn on a different controller and execute that for a little while until I get roughly back into the region of my original controller, and I'll turn my original controller. This is really bad for Wei, sorry. Right? There's some, it sort of feels natural that I could have different controllers that turn on for different parts of the state space, right? And maybe this is sort of like thinking about skills, different skills, and like for the Boston Dynamics robots, where we have a trot, we have a bound. Those are different skills that we can turn on and off. We probably have a skill that transitions from trotting to bounding. That'll somehow be a funnel that takes me from somewhere in my trotting region of attraction over to somewhere in my bounding region of attraction. Even for the pendulum swing up, right? So when I showed this picture here of of that, right? Looks kind of like I think that's kind of a gross controller. But there's something that it did have to do something fundamental, which is even for my torque-limited pendulum to swing up to the top, we know that the optimal policy, or this is not an optimal policy, this is just a sufficient policy, but we know that the solution is going to have to be a little bit ugly. Remember, there's some state here where I could maybe get around in, or 2 pumps, and there's some neighboring state here where maybe I could get around in 1 pump. So there's some fundamental discreteness that I think has to come out of your controller. You have to somehow make a decision. I'm doing 1 pump right now and trying to go for the goal, or I'm doing a 2 pump thing and try to go for the goal, right? And this somehow those decisions are captured in being in these different funnels in this. And if I were to write a controller down that had a finite state machine which says I've got 1 pump left to go, I've got 2 pumps left to go, I've got 1 pump left to go, and had to do a transition through that, the control design I'd have to do is complicated. It's hybrid. It's going to be a more complicated control. We don't actually. I haven't seen that work well. This comes up with sort of a hybrid, switch into these different controllers automatically with only smooth analysis on the smooth system. There's something I think that's maybe good or right about the system having made a discrete decision by virtue of being in one of the funnels. You notice the funnels overlap, and the rule is once you're in a funnel, you keep executing that funnel until something kicks you out and your model was wrong, I had to do something else. So there's some integer state there. There's some discrete decision that was made to be in this funnel, and this is what I'm doing right now. And I think I don't know simpler ways to encode that, but I think it's important. I think it's important because I think most of the controllers that people write by hand that work well for these kind of tasks, they do have state machines in them. But I haven't given a lecture on how to synthesize state machines because I don't really have that, right? But except maybe somehow here. Okay, so that's how I think about it, is that there's a bunch of skills that you'd like to somehow be able to choose between. How do you automatically make skills in new parts of the state space? Well, if the goal of a skill is to get me back to another place where I know, then this is a recipe, and that sort of it fills up the space. Okay, there's a couple other variations of this that may be useful. So the one thing we immediately didn't like about this was that it's an offline control design. So if I have runtime constraints, that's no good, right? If I'm like, now I'm going to apply this to a plane flying through the forest, okay? I didn't know where the trees were when I was using my sums of squares optimization, so that's rough, okay? But So the recipe for real-time planning, online planning with sort of these robust funnels is that you build a library of possible things you could do. So the quadrotor could fly straight, it could fly and bank a little bit and straighten out, fly or bank a little bit, and you can imagine just sort of a library of possible funnels where you can go to, and then you can pick between them. You can pick from those funnels at execution time. So now, just like for Emilio's controller, Emilio Frizzoli, I told you about his RRT version where he did the controller by solving value iteration for the helicopter with no obstacles, and he used that to do planning when there were new obstacles. Here, the dynamics are known ahead of time, maybe with uncertainty if the wind is blowing or something, but I can compute those funnels a priori, and then check if they would be valid, if they're a valid certificate at runtime, okay? And the thing that makes that, this is the, so here's one funnel. Ani worked really hard on that video, so, okay, but you don't want to have an infinitely large library of funnels to work through every possible nook and cranny that you're going to find in whatever polygonal forest you happen to be flying through. So there's a slight twist on what I was just saying here that allows you to be sort of more useful at runtime. Okay, so we talked about verifying finite time invariance. So there's sort of two extremes here. So if this boundary here is V or J, if it was came out of the Lyapunov function, this is defined by the sublevel set of my time-varying Lyapunov function, right? Where this was just my from LQR, for instance. Okay, that J is 0 here, right? And my claim is that if you're asking for this for all x, where J of x less than or equal to rho of t, that's actually kind of a hard thing to do because this might not be a feasible solution down to numerical accuracy on my trajectory. So I said instead, just say that this is true for all x, J of x, t equals rho of t. This is full-on stability. My claim is we might not have it. This is just finite time invariance. Okay. If I could get stability, then I can do what I've shown here, although that cartoon looks a little funny, but this actually, if this is certified everywhere, then it also happens to be the case that every sublevel set of my, if I'm always going downhill, J dot is always less than or equal to some, I have to change that just a little bit, but I can verify that I'm always going downhill here. It would have to be this or 0, right? Or I can scale alpha, I can say that every sublevel set J dot less than some scalar times rho dot. If I prove it for all inside the state, then I can say that every sublevel set is also an invariant set. So if I now at runtime have a new possible collision, which invalidated my original invariance proof, there might be a sublevel set here that is still valid. So if you've done this one, which I said was hard to do, then you can actually trim your funnels at runtime. Awesome. But like I said, it's hard to do. This one was easier to do. So in practice, what do? We try to verify it for all x where, let's say, or even, I can just say that, where this is some scalar So I can try to get a stability property that's valid like in a donut around the trajectory, right, which allows me to shrink to some extent, but doesn't shrink to the point where I get into the numerical tolerance issues of the actual trajectory. So you'd like to say that all sublevel sets between 1 and, let's say, 0.5 are invariant sets. And you can write that down too. So there's a trade-off between, between basically the numerical tolerance of your algorithm and how much you can sort of trim it at runtime. But once you trim it at runtime, then a relatively sparse set of those trajectories, of those motion planning funnels, can be used to sort of fly through pretty arbitrary obstacles. So this is Ani with first, in a motion capture arena, fictitious obstacles. So that's just added by the animation, but the robot pretended it didn't want to hit those things. So we'd only tell the vehicle about the obstacles after it was off the launcher, and we have a lot of crossbow launchers because we want to get up to speed quickly before the end of the runway. Okay, and then he got brave enough to add real obstacles, PVC obstacles, and showed. He could fly through obstacles, he had a sufficient library that he could provably robust fly through obstacles that were not known until runtime. One time he clipped his wing a little bit, but he really just set these up and kept flying them, flew through little hoops, flew through an MIT. That's what you have to do, right? You guys, if you haven't done it yet, you'll make a robot video with an MIT in it before you're done. So he, in that experiment, in order to really guarantee that we never left the funnel, he actually did the robust versions of the funnels where there was uncertainty in the dynamics, and so it was conservative about the absolute proof of the funnel in case the model was wrong. Okay, so it was actually doing the robust control version of this, but somehow robust control often gets a bad rap because people say if you do robust control, then you sacrifice performance. Once you ask for robustness and worst case analysis, then you can't do sort of high performance tasks. You're just too conservative. And somehow this found a nice balance. I think it was a nice way to show that you can have some provably robust behaviors, but you combine them in the sort of library approach and you can still do pretty aggressive things. Okay? Okay, so if I had more time, let me just tell you what I didn't tell you. But the last sort of piece of this puzzle is that the number of funnels you end up adding, it roughly depends on how well your LQR controller works for the nonlinear system. And you can also, in the sums of squares iteration, search for better controllers at the same time. Okay, so the way that works is you parameterize. I can do the very cartoon version here first. So if I say x dot is f of x u, right, this was a polynomial, let's say, but let's say it's even control affine. And I want to search for a controller u equals, let's say, negative kx, or the generalization of that, which is some polynomial, let's say negative k times a bunch of monomials of x. Okay. Then let's say I'm given v, my conditions v dot of x just look like partial v partial x, f1 of x plus f2 of x, k m of x. Right? V is given, then the search for V dot of x less than 0, for all x, where V of x less than or equal to rho, is actually still, if I lock in rho, it's still convex in K. Okay, so I can actually use sums of squares to search for rho and K simultaneously. What I can't do is search for K and V simultaneously. So in practice, there's a handful of ways where you pick a controller K. For instance, you start it with LQR. You search for the biggest Lyapunov function that'll prove the biggest basin of attraction. And then you lock in your Lyapunov function and said, could I have found a different K that would have proven an even bigger region of attraction? And you alternate back and forth. So you get bilinear alternations. And this can make a big difference in practice. So for just doing LQR trees for the Acrobat, this is, theta 1, theta 2, this is a projection of a 4-dimensional funnel onto a 2-dimensional picture, but it's hard to interpret pictures of funnels unless they're in the full space, but still. Little itty-bitty LQR basin of attraction, really pretty big polynomial basin of, if you optimize the controller and the Lyapunov function simultaneously, you can find a balancing controller at the top, which is just a polynomial, which is a lot bigger region of attraction than the original LQR controller. Okay, which then means, of course, you've got a bigger region that you can land in. All of your trajectories can be potentially bigger. Similarly, along the trajectory, you can iterate between K as a function of time and S and do better in the sort of trajectory optimization funnels. So, the blue was the LQR funnels. The S, this is this weird kink, which I could explain, but that can make these bigger and better. So that is, and there are a few different versions of this that I'll try to make sure are cited nicely in the notes. Okay, so you can make bigger and bigger funnels, and that's good. But there's one thing that I just don't like about this at all, which is the reason we don't use this, for instance, for manipulation. And I think it is good for vehicles. I think it's good for acrobats and cart pulls. I don't think it works for manipulation. And the fundamental reason is that we're still, so far, stuck in full state feedback. These controllers work, they depend critically on the notion of what's the state space. Write a state estimator and figure out where I am in state space, and then pick which controller I'm going to run based on being at that point in state space, or that region in state space. And I think that's one of the biggest limitations in where we are in the field right now. And the reason I've turned my attention mostly towards manipulation now is because I think manipulation finally forces you to change that thinking. It just doesn't make sense to assume you know what the whole world, the state of the whole world, in order to make a decision for manipulation. So if I wanted to button my shirt, I shouldn't have to know the full state of my shirt to do this button, right? There's something just that doesn't quite work here, right? Or if I'm reaching in my pocket to pick out my keys and I don't want to pick out my credit cards, right? Then somehow I've got controllers. I think the paradigm of feedback motion planning, good. Having skills that do individual things, I like that. I think that's natural. I probably have a reach in the pocket skill. I've probably got a pretty bad juggling skill. I've got a bunch of things. But I probably don't map the whole world's state into a particular thing to decide which skill to execute. So, more work to do. Yeah? Cool. So keep asking questions in lecture, but even about your projects. Looking forward to the project check-ins tomorrow. I'll try to answer as fast as I can on Piazza or whatever. See you Thursday.